In this video, we're going to take a look at the applications of exponents. First, quite common in science and mathematics is scientific notation, and we're going to convert from standard to scientific and from scientific to standard notations. It helps us, scientific notation really helps us take really small numbers or really large numbers and makes them something that we can work with easier. And then we're going to use properties of exponents to solve some real-world applications as well. First, scientific notation. This is going to be a positive number that is a product of a number a, where a is between 1 and 10. Notice it can be 1 because it's or equal to, but it cannot be 10. Basically what we're looking for is a non-zero one-digit number with a decimal point that follows, and then other digits would follow the decimal point. And then it'll be raised to an integer power r of 10. So a times 10 to the r power. An example would be like 3.752 times 10 to the 7th. That would be a way to write scientific notation. Okay. There's kind of 3 steps here to write a number in scientific notation. We move the decimal point in the original number so that the new number has a value between 1 and 10, including 1, not including 10. Then we're going to count the number of decimal places the decimal point moved in step 1. If the decimal point is moved to the left, the count will be positive. And if the decimal point is moved to the right, the count is negative. Multiply the new number in step 1 by 10 raised to the exponent equal to that count that we did in in step number 2. So the number of decimal places is what we were counting, and so here we go. Write each number in scientific notation. I need a one-digit number that is not 0. So in that case, 3 here, 3.8. All the rest of the digits are zeros. We will not include them here. That's not necessary. We're going to count decimal places. 1, 2, 3, 4, 5, 6, 7, 8 decimal places. So this is times 10 to the 8. What we have to figure out is it positive 8 or negative 8? According to the steps that we just went through, we moved to the left, so it is positive 8. In letter B, remember it's a single digit we're looking for that's not 0. So this would not be written in scientific notation now because the 0 is separated by the decimal point. We need to bring the decimal point just after the 3. So we have 3.014. Here this 0 matters because there were other numbered digits that followed. Times 10 to the 1, 2, 3. And this time we moved to the right, so this is negative 3, the exponent. In example 2, we're given scientific notation and we need to convert back to standard form. So we have 1.85 is going to be 185, and we move the decimal 3 places to the right now. See, this is a positive exponent, meaning we moved to the left to get to scientific notation, so we're going to unpack that and go to the right now, 3 places. 1, 2, 3 places is where our decimal would go. After this 0, we do not need to write it in this case because there are no digits that follow, just another series of zeros. Letter B, 1.7 times 10 to the negative 4. This time we're moving to the left 4 from between the 1 and the 7. 1, 2, 3, 4 is the decimal point, and we will need to put a 0 in front just to keep it nice. We should always have at least one digit in front of the decimal point, whether scientific or standard. If it is standard notation, a 0 is allowed in that place. Now we're going to perform some operations like multiplying and dividing scientific notation numbers. You'll see this is very similar to operating with the properties of exponents. So we have 1.2 times 10 to the 4th times 3 times 10 to the 15th. 1.2 times 3, those were both constants. We can multiply those and get 3.6. Now we can also look at 10 to the 4th times 10 to the 15th, and we see that we're multiplying same base. So we're going to add exponents. Times 10 to the 19th, and we usually use the X symbol in scientific notation for multiplication. We check to see that we have one digit in front of the decimal place. We are good to go. In letter B, 7.2 times 5.4 times 10 to the negative 7th times 10 to the 17th. 7.2 times 5.4 is 38 and 88 hundredths times 10 to the 10th, because we're adding exponents since we're multiplying same base again. Negative 7 plus 17 is positive 10. The temptation in a question like this is to stop here. But this number here, 38 and 88 hundredths, is not set for scientific notation because 38 is not between 1 and 10. It's not a single digit number in front of the decimal point. So I need to move to the left one place to give us 3.888 times 10. And now we have to think. We moved the decimal point to the left to get scientific notation. So it's going to be positive exponent, and therefore we're going to add one place that we moved it to the 10 that was existing and have an exponent of 11. This now is written in scientific notation. So don't fall into that trap. Just after you multiply whatever the number is, you write that as your answer. Just make sure that it's one digit, then the decimal point, and the rest of the digits follow. Now to divide. Again, just like with the properties of exponents, here on the right side of this problem we're dividing the same base, and we would subtract exponents. So this is 10 to the 25 minus 10, or 15th power. And we're going to kind of separate with the multiplication sign. On the left side, 6.4 divided by 3.2, that's simply 2. Now it's best to still write that decimal point and at least 1 0 because we're in scientific notation. Even though there were no other digits that followed, it's good to have at least the 1 0 when a whole number was the answer. We separate again in letter D. 2 divided by 8 is 0.25, and 10 to the 13th divided by 10 to the 16th equals 10 to the 13 minus 16, so times 10 to the negative 3. Again, that temptation, just like in letter B, is to stop here, but a 0 is the number that's in front of the decimal, and that's not okay, so we're going to move to the right one place to have 2.5 times 10 to the, we moved to the right, so this is going to be negative 1 that we're going to add to that negative 3 and have an exponent of negative 4. And just to kind of show you kind of why and or how this works in the scientific notation realm, if we were to convert both of these to standard form, we would end up with the same answer. See, a negative 3 tells me to move the decimal point to the left here, 3 places, so 0.123325. And here we're going to move the decimal point 4 places to the left. 1, 2, 3, 4. It's going to give us 0.1234. So the decimal in the second example, or the second answer, was here to start. In the first it was here and moved 3 places. This one moved 4. And you see the answers are the same. As I said earlier, scientific notation is often used to make really large or really small numbers more manageable. The moon is approximately 2 4/10 times 10 to the 5th power miles from Earth. So if we look at this in standard form, that'll give us some more context, and you'll see, how large this number is. We're going to move the decimal to the right because this is a positive exponent 5 places. 1, 2, 3, 4, 5. So it's going to be 1, 2, 3, 4 zeros after 24. So the moon is 240,000 miles from Earth. Example 5. An August 2011 report noted that Facebook has approximately 250 million photos uploaded daily. So how many photos would that be in a year? So each day, 250 million photos. And now that is done for 365 days. This is going to be a very large number. To be able to do this problem, the math is set up for you. I've scaffolded it in letter C. We first need to make our numbers a little bit more manageable, so we'll go scientific notation. 250 million. That's 250 million. In scientific notation, we're going to move the decimal 1, 2, 3, 4, 5, 6, 7, 8 places. So 2.5 times 10 to the 8th. Since we originally moved left, this is going to be positive 8. In scientific notation, 365. We're going to move the decimal 2 places to the left, so again a positive exponent since we moved left. 3.65 times 10 to the 2nd. Now, the reason, 365 is not a very large number. The reason we're going to write that in scientific notation is so that the multiplication step could be a little simpler. 2.5 times 10 to the 8th times 3.65 times 10 squared 2.5 times 3.65 is 9.125 times 10 to the 8th times 10 squared. We're multiplying same base, we add exponents. This is times 10 to the 10th. That's how many photos would be uploaded yearly on Facebook according to that 2011 report. I'm sure today that number is drastically different. Now we're going to look at some other real-world examples of using exponents. And the first kind of category or type of question we're going to look at is compound interest. So we're going to look at some financial problems. This formula, A equals P times 1 plus R divided by N, that quantity raised to the NT power, gives the amount of money in an account, whether a bank account or like a savings account or a certificate of deposit account, after an elapsed time. I've defined those variables for you here. A is the amount after T years. That's important. It's not, if they gave you months, you would have to convert that number to years to substitute into T for this formula. P represents the principal, or your initial amount. R is the rate of interest, and we always will write that as a decimal. And so in these examples, we'll explain and kind of look at that in a little bit more detail. Then N is the number of times that they will compound the interest per year. And again, that will make a little bit more sense in a moment. And again, T is the number of years. Remember, T has to be years. Again, stressing that to you. Example 6. Determine the amount in an account which someone invests $100 after 4 years at 3% compounded monthly. In word problems that involve formulas, it may be helpful to, as you're understanding the problem, to organize your information. So I'm going to take all of the given information plus what I'm trying to find and sort of put that over here in a box. The amount is what I'm looking for. If I invest a principal of $100, that's the starting amount, at a rate of 3%. Remember, I said that has to be written as a decimal, and we take percents, move the decimal 2 to the left to then write that as a decimal. So 0.03 would be equal to 3%. Percent means per 100. 3% would be like 3 pennies out of 100 pennies, or out of $1. That might be a way to help remember to move the decimal point to the left 3 times. The time is 4 years. Again, that needs to be in years. And they say we're compounded monthly, so N is going to be 12. Because there are 12 months in the year, the interest is going to be calculated 12 times. Okay, so that's the given information in this problem. I like to put that in a box. And then I usually will rewrite the formula. A equals P times 1 plus R over N to the NT. And sometimes I'll even box that as well. This formula would use all of the variables that were given. So that's how I know this is the formula to use. And now we'll substitute what we know. A equals $100 plus 1, or times 1 plus R was 0.03 divided by 12. to the 12 times 4 power. Let's explore why we're dividing that interest rate by 12 times in the year. Okay, so if the bank is going to calculate interest at the end of each month, they're not going to give you 3% every single month. At that point, you would earn well more than 3% total at the end of the year. So we take the 3% that they say they'll give you over the year and divide that percentage by each time they compound it. So in this case, 12. So the actual percent that you will get each month is less than 3%, but we compound interest on the total amount in the account. So every time we're compounding the interest, the account is worth more, like it's at a larger amount of money that we're compounding the interest on. So you do actually end up getting more than 3% at the end of the year total, even though you get much less than 3% each month. So we'll simplify inside the parentheses first, as well as multiplying the exponent. So 100 times, this will be 1.0025 raised to the 48th power. Now we have to raise 1.0025 to the 48th power before we can multiply by 100. And that will be 1.127328021. This is what your calculator would tell you. You don't necessarily need to write out all of those digits, but as you're following these steps, but you should continue in the calculator with all of those digits by just hitting times 100. So it'll take that answer that you already had, multiply the whole thing by 100, and that will give you $112.73. At this point, you can round to the nearest penny. Any decimal point after that really doesn't make sense when dealing with money. So by investing $100 for 4 years at 3%, you would earn $12.73 in interest. Number 7. Determine the amount in an account in which someone invests $2,000 after 20 years at 1.5% compounded quarterly. So again, we're trying to find the amount in an account, but this time we're investing a whole lot more than $100. We're investing $2,000 at an interest rate of 0.015, because again I moved the decimal place 2 places to the left. This is going to be for a time of 20 years, and it is going to be compounded quarterly, which is 4 times a year. There's our given information. Again, it's helpful to write the formula until you have it memorized. I'm not going to write that again here, but I encourage you to. We substitute what we know. A equals 2,000 times 1 plus 0.015 divided by 4 to the 4 times 20 power. So 2,000 times, simplifying what's inside first by dividing 0.015 by 4 and then adding 1.00375 raise that to the 80th power as you multiply 4 and 20. We take 1.00375, raise that to the 80th power. Again, in your calculator, you do not need to write out all of these decimals on your paper, but keep them in the calculator. 1.3491011617, and that is being multiplied by 2,000 now. Now you can multiply. So if you just take that answer that's in your calculator and hit times 2,000, it will multiply it unrounded. It's a very good habit to not round in the middle of a problem, only at the end. That way you'll be most accurate. $2,698.20 rounded to the nearest penny. Okay. The next set of examples we're going to look at are some geometry problems. In the first geometry question here, we're going to look at a cylinder, particularly its volume. And I've given that formula to you here, so you don't need to remember that from the past, but will work. And then you're going to define R as the radius of the base, which is a circle in shape, and H is the height of the cylinder. They tell us that the height is going to be 7 times x squared meters, and the radius is going to be 3x meters. And we've shown that on the picture as well here. So in the first part, we want to write the volume as a simplified expression in terms of x. More times than not, students will write just a substitution. The substitution of what was given into the given formula, but they will not simplify. This is what's asked in this question, and it's very important. Please remember to simplify so that you can get full credit on your quizzes and tests. Volume is what we're looking for, equals pi times the radius squared, and the radius was given as 3x squared, times the height, which was given as 7x squared. Alright, so we've got several things to do here. First, we need to square everything inside this parenthesis because the square, or that exponent of 2, is outside. So we need to have 3 squared and x squared. Well, 3 squared is 9, x squared. We still have pi involved. The 7 is not squared because only the x is squared, with that exponent 2 being inside the parentheses and attached to the x. So the 7 will stay alone as 7x squared. We're multiplying all of these things now. 9 and 7 are coefficients and can be multiplied to be 63. Then we usually write pi. Then we usually write the variable x squared times x squared. We add exponents, we get x to the 4th. So this is the expression, and of course we want that to be equal to v, so we could have that simplified as a nice formula to be able to substitute in part B the information. Approximate the volume to 2 decimal places they want. So we will make sure that we round at the end to 2 decimal places. When x is 1.5, so we're going to take 1 5/10 and substitute into our formula for x. 63 pi times 1 5/10 to the 4th power. When we raise that to the fourth power, we get 5.0625. That's being multiplied by 63 pi. And on your calculator, you should see a pi key if you're using a TI-83 or 4. I believe that is above the caret symbol on the right side of your calculator. And then when we multiply all of those together using the pi key, the volume is going to be 1,001 hundredths feet cubed. Since we're talking volume and we were given this information in feet, cubed is the 3 dimensions dealt with in volume. So hopefully in this video you've seen how the properties of exponents from the previous video can be applied with scientific notation, particularly when multiplying or dividing scientific notation numbers. Also in some real-world applications with some different formulas, whether it be a geometry scenario or compound interest, and there are many others, but the properties of exponents from our first video, again, are so important to know, so that when you're faced with problems like this, you're able to easily navigate through them.